Thank you very much for the nice introduction and for the invitation to speak in this nice seminar. Although I'm not directly working on photothermal applications, but on problems related to this field, and also maybe some of them related on a fundamental level. So let me show you the first slide, which is the title slide. And there you see that I'm working on hot Brownian particles, so Brownian particles that are heated often by a laser. And you see on the left a little video, microscopy video that was taken in Frank Zicho's lab, who is one of my main collaborators in this whole field. And you see that this is a Brownian particle that's undergoing Brownian motion. But if you switch on the laser at some point, it will still do some sort of Brownian motion, but a much faster one. And this is true no matter whether that's a little gold particle, let's say, or whether it's a Janus particle, which is only half gold and half polystyrene, for instance. You get an enhanced thermal Brownian motion, and we would like to understand this motion and also understand how to deal with such objects on a coarse-grained level without, going to a complete microscopic simulation or something of that sort. And apart from Frank, the main collaborators are Viktor Olubac from Prague. He has some time ago been a postdoc in my group, coming with a Humboldt fellowship. Gian Maria Falasco is in Padova, and he contributed a lot to hot Brownian motion. He's now has his independent research group there in Padova. It's also in the group some time ago. And I will also mention the recent work with Sarah Loos, who is in Cambridge, working with Mike Cates there. And she spent half a year or so in the group recently. And below you see also some names of PhD students, some people from my group who have also contributed to some of these subjects that I'm talking about. And the main theme for me is nicely comprised or expressed by this quote here from Eric Smith. And he says, "The ability to coarse grain has been our most important tool to bring an infinitely complicated world within reach of analysis and comprehension." And this task is usually not so difficult as you might think if you are in equilibrium. Because then we have a lot of constraints that allow us to scale up from a microscopic Hamiltonian to a macroscopic Hamiltonian, which is then usually called a free energy, and which has a hugely reduced complexity, but is nevertheless is very useful because it rules the macroscopic world. Now, if you are thinking of your photothermal applications, you are heating some local devices, some tiny nanostructures, some nanoparticles or microscopic particles. And automatically you are out of equilibrium. You do not have a constant temperature anymore. You do not have a Boltzmann factor anymore. So this nice program of coarse graining up to a larger scale is seriously jeopardized by all of these applications. And so we are asking if we have many body systems or just complicated micro nanostructures that are driven far from equilibrium on a small scale, on a particle scale, say, can we still find useful coarse grain theories as we are used to from our textbook examples of thermodynamics? Or have we to give up and say, okay, the only thing you can do in theory is simulate the whole complexity bottom up, and you can't do anything else? So that's the main question. And so the first thing I want to describe to you is hot Brownian motion. So if I have a nanoparticle that is heated by a laser, it is hotter than the surrounding fluid. And so here you see in red a temperature field surrounding the particle, and also the viscosity will not be constant around the particle. And so the first thing is, if we want to describe such a hot particle in the usual way with the diffusion equation or a Langevin equation, we realize that this is already a coarse-grained description, but we have to take a step back into the details of the non-homogeneous or non-isothermal solvent now, and understand how we arrive at the usual equations for such a particle. And we can still write down the usual Langevin equations or diffusion equations for such a particle, but with effective parameters. So we need an effective friction coefficient, and we need an effective viscosity, and we need an effective temperature. And if we have all those things, then they nicely also obey an Einstein relation as usual. But the question is, can we calculate these all these effective parameters of the system? And the answer is positive. That's something we've done over a couple of years, around 10 years ago. And yeah, you see one of the answers here. Yeah, you can describe such a hot particle as a normal Brownian particle with an effective temperature. It's called here the THBM for hot Brownian motion. And it is higher than the surface temperature of the particle, which is here T naught, by some certain amount that in first order, if you don't heat too much, it's a universal constant. And if you heat very strongly, then also the solvent properties and the viscosity and so on enters, and it gets a bit more complicated. So that's a relatively positive answer. You can do such a thing. You can have a coarse-grained description of the system with some effective parameters, and you can calculate some of them. It gets a bit more complex if you want more if you go to more complicated situations. But on this simple level here of one such hot particle, there's a beautiful comparison here on the right. That's a paper by Markus Semke and Frank Zichos, and they did first they invented a method that allows to make a parameter-free test of this theoretical prediction, and then they tested it and they found a nice agreement. So they looked essentially how long the particle stays in a laser focus, and with this twin Fox method, which is itself exploiting photothermal physics, they were then able to show that this is really truly a useful description. Depending on how much they heat the particle, it gets faster and faster, and it is really predicted by by these equations. Now, if you ask, okay, that's for the positional Brownian motion, but what about the rotational Brownian motion? Then you realize, okay, there you need another temperature, which you also can calculate. But you realize that if you go further in this direction, you will have more and more temperatures, and it will be more and more difficult to really know how to properly apply these things. But you can go quite a bit in this direction. And so one thing you see here is, if I have a gas of such hot Brownian particles, I could describe them with a Boltzmann factor. And the nasty thing here is that I've at least two temperatures now, one for the positional degrees of freedom, and you see for the velocities I have another temperature. But I can calculate both of these temperatures. The first one would be the one that I've already written down. The second one looks more complicated. I just to impress you. You see, here is a formula how you calculate the temperature for the velocity degrees of freedom. And you see, okay, these things can be done to some extent, but they get increasingly complex. Also, if you want to have something like a fluctuation dissipation theorem for these hot particles, if you push them or pull them through the fluid, you can do this, but you end up with a temperature spectrum, T of omega here. So not one effective temperature will, in general, for all frequencies or all speeds, not solve your problem, but but you will have a more complex quantity to calculate, and this is similarly complicated as the TV that I showed you, but it can be done. So you can go quite a bit in this direction and exploit physical structures that are very similar to the ones that you know from equilibrium physics, but with effective coefficients that are for single spherical particles even exactly known. Now, so we understand these non-equilibrium, non-thermal fluctuations for this simple problem, but of course, you can imagine that you have something else than a sphere at some point. For instance, the Janus particle that I mentioned before, and then a hot particle will automatically become a swimmer. And so that's the second comment I want to make here. So non-symmetrical hot particles, or even hot particles in non-symmetrical environments, will become swimmers. So they will move around with a self-propulsion or directed motion. And as you saw in the video that I showed in the very beginning. And then you can also, for those particles, characterize the thermal fluctuations, and you get more effective temperatures and so on. But as soon as they start to interact, if you have more than one and they come into interaction, then it gets pretty complicated. So you get then quite complex effective attractions and repulsions and all kinds of things between the particles, which are not even symmetric between the particles. So if one particle affects the other one not necessarily affects the first one in a reciprocal way, but it can be very complicated, it can be very asymmetric. So there is a complex set of interactions then between hot particles, and here in the example you see a paper we did together with Frank Zichos again, where there is one hot source, a heat source, a gold particle, and the other particle is a Janus particle, and we try to make sense of all these complicated directed interactions between the two. Now, still, if you look at one particle, you can describe it very well with a Langevin equation again, as you would for a normal Brownian particle, except now you have these effective coefficients, effective temperatures, effective friction coefficients, and so on. And you have on top now the self-propulsion of the particle. So here this is represented by the Vp, it's the self-propulsion speed of the particle, which depends on your illumination. If you illuminate more, it will be faster. Less, it will be less, or if you switch off the laser, it will not move and will just be a Brownian particle. And it's also rotating, of course, and with another effective temperature and so on, as we discussed. But you can do a lot also on this level. Here I show some examples from Frank's lab again. In one particularly important thing that he exploits a lot in his work is that he can nudge these particles, so he can watch where they want to go if he switches on the laser light, and only if they look in the right direction, he switches on the laser light, and then they swim where he wants them to swim. So that's the photon nudging, and we have exploited this a lot in our joint work. So if one has such a description, one can answer some questions that people have posed and claimed that they are hard to tackle. Here is an example, a nice physical review letters from Cambridge people here from some years ago, and they asked the question, how far from equilibrium is active matter? And then they say, this is hard to answer, but a very good way is to look at the entropy production rate, because that quantifies the breakdown of time reversal symmetry, and that tells us how far we are from equilibrium. So we have a metric to determine how far we are out of equilibrium, and that's entropy production. But then they say, yeah, this is in principle is a very smart thing, but it's hard to compute and even harder to measure experimentally, and it has been little studied in active systems. So when we saw this, we said, well, we can of course do this with Frank, and we can also, Gian Maria did the calculation from the theory. So if you have a hot swimmer, we can look how it swims, and sometimes it goes in the direction of swimming, but sometimes there's a fluctuation that makes it go backwards, and we can look how often is it jumping forward as it should due to the swimming, and how often is it jumping backwards due to some random fluctuation, and we can quantify that, and then we can check such a fluctuation theorem as written here, where you compare motion that goes in the right way, so to speak, where entropy is produced, to motion in the wrong way, where entropy is reduced, and you quantify the probability for going right or wrong directions for such a particle, right? And that's essentially exactly what they had in mind in this paper here, and that's exactly what we did. So we had this Janus particle, and in Frank's group, they looked at long traces of these particles in the lab, and we did simulations and looked again at long traces of these particles in the computer. And we also did the calculation of what to expect for these forward-backward fluctuations of these particles. And then you take the logarithm of these probabilities, and then you see that they should fall in a straight line depending on what your speed is with which you drive the particle. And you see here we did a very nice, again, parameter-free check of these relations. They are linear relations, and what we did not explicitly do here, but what could again be done, you should then again use your effective parameters, your effective friction, effective temperature, and so on, to quantify the slope of these lines. Yeah, and another thing that we did on this with this system is that we what I think we checked for the first time, like Frank's group, of course, did the experimental work. So there was the first experimental check, I think, of a thermodynamic uncertainty relation, which is saturated here in this particular example. So we can do experiments and also simulations, of course, of such systems, and use them to check predictions from stochastic thermodynamics that other people think very hard to do. And so active matter and hot active matter or hot particles can be essentially very good tools to check such theoretical predictions that people have made. And it went a bit further compared to what I show here. Also, we did something on the angular distribution and so on and so on. So it was yet another prediction from another group and so on. So you can do quite a bit if you employ these systems as paradigmatic non-equilibrium systems for such general and check such general predictions. You need to somehow, of course, have control over your microscopic parameters, these effective temperatures and effective frictions, and so on and so on. If I have a bit more time, I don't know, 2 minutes or
yes, 2 minutes.
I mentioned a few more things that we did. If you have these swimmers, hot swimmers, you can, for instance, ask the question: can they be used in an active heat engine? A heat engine not operating on passive gas or something or fluid, but on an active system. And what does come out of this? And then and another example down here is activity patterns, like activity landscapes. So you could speak of potential landscapes in which these active particles move, or activity landscapes in which they move. And both of them lead to very interesting predictions and new results. And unfortunately, I was a bit slow in the beginning. So let me jump over this bit and say what people have claimed a lot is that with active heat engines, you may be able to overcome the second law of thermodynamics. That is not true, of course, but the essential thing that is new here with these hot particles is that you break the zeroth law of thermodynamics. So the zeroth law of thermodynamics is violated, and that's why you can get very interesting effects, in particular in heat engines. But the second law is still must still be verified, and the essential tool to check that it is verified, and also the essential tool to understand how an active heat engine works and what active heat means at all, is again this concept of an effective temperature that you have to calculate then in this situation. And for this active heat engine here, which is based on an active Brownian particle, this could also be done in all detail. And Victor has done this and written a very, very nice paper on this. And this now very much cited, and many people work in this field. And if you ever have to connect to it, maybe go back to Victor's paper, because some newer papers that they do cite him, but they have not understood everything, I guess, that is said in this paper. So there is still quite often limited understanding of these fundamental issues here. Okay, then maybe the last short thing here is, if we do not have potential forces like a piston or so in a heat engine, but we have just activity landscape, where some region there is activity, in some region there is no activity, and we have a Janus particle going through that, then we get very interesting patterns. So we get accumulation of particles in the passive region and depletion in the active region, and we get interesting polarization patterns at the boundaries. Whenever there's a gradient in activity, there is an interesting accumulation also of orientation, so of polarization of the particles. And this is a bit like, you can do calculations that resemble a bit what you do in quantum mechanics. If you have a potential well, and you want to calculate the wave functions, a bit like this, and you can do all these calculations. And Sven Auscher has done a lot there with Victor Olubach, and so you can characterize all these distributions in such a static, active, passive landscape. And in particular, one intriguing thing is that if you give your passive or active region a strange shape, you get ratcheting. So you have only a static activity landscape, no potentials, and you put particles that swim in the active region and just diffuse in the passive region. And then you get ratcheting. So you get a directed current out of this because you break the symmetry, but you need at least 2 dimensions to do this. But then you can build ratchets, active Brownian ratchets, so to speak. Yeah. Okay, and so maybe the last thing I just skipped, that the last I wanted to say is what we are currently doing is we are exploring if we go from the particle description to a many-body theory, then normally in physics, every many-body theory becomes a field theory in the end. And so the question is, can we go this step, and can we, for many-body systems that are locally out of equilibrium by heating, by photothermal effects, whatever, can we devise field theories for those, for the critical behavior, the phase transitions, and whatever of these many-body systems? And that's currently ongoing work. And with this, I come to my summary. And since I'm over time already, it seems I stop and just leave the summary as such. And I'm happy to take your questions, of course. Thank you very much for your attention.
Thank you very much for your nice talk. it is good to see that a lot of developments happens on the hot Brownian motions.
Yeah.
Pretty much. So it is open for question now. I see already Fang has a question.
Okay, I have to.
That was essentially just applause and not a question.
Okay, good. So people, please write down in chat, or you can also directly ask the questions.
Yeah, I'm currently not seeing the chat, but maybe.
Okay, I can ask. Yeah, yes.
Okay.
It's no wonder. Yeah. So I have a question. Is that so? We are actually Meso Lab was quite interested on the hot rotational motions, and I feel like when you have anisotropic particles, and it becomes much more complicated because it has a time-dependent absorption. So that means you have a not only spatial viscosity change, but you have a temporal change of viscosity. And so if you have a complicated shape of the particle, still this your new development with this velocity consideration, will that work? I mean, for a simple example, one can take it as a nanorods.
Well, okay, the general answer to this is it gets very complicated, as you said. And that is also, like if I have a sphere, I have a simple law for if I drag the sphere through the fluid, Stokes' law. If I have a cylinder, it gets more complicated. I have to say, it depends on the direction of the cylinder and whether it's rotating or translating. And so you get a lot of friction coefficients already, right? And now if we go to hot cylinders, for instance, then this complexity of the friction coefficients, you also it's repeated basically for the temperature. So you get different effective temperatures for different degrees of freedom. What we have checked is that these effects are pretty weak, most of them. So the biggest effect is always this effective temperature effect, like the first order effect. And then if you say, well, my particle is not completely isotropic, it's not a perfect sphere, then the question is how much is it not a perfect sphere? So if you have an aspect ratio of 100, then you start to see deviations, small deviations, and those can be captured as far as the temperatures are concerned. And the friction effects are even lower effects. So you would mostly, be worried, I would say, about if I get a very, very extreme aspect ratio, whether I have to think of special effective temperatures, which are not those of the sphere anymore. And we have written a paper on some aspects of that. And usually they will, for practical applications, they will probably be enough for many things. But as you say, I mean, once temperature has become a tensor, it's kind of painful, and the question is how far do you want to go with that, right? You can hire an engineer maybe who calculates this tensor for you and does all the job. But the question is how much money do you want to put into this?
Thanks. I think we have a question in chat from Ode Barbara. What happens to the expression on THPM for large delta T?
Yeah, for large delta T, I mean, as long as the fluid doesn't boil, let's say, right? For small delta T, there is a universal expression, and maybe I should go back here to this. We had this here, So you see, the T naught is your ambient temperature. That could be 300 Kelvin. Now the delta T is how much you heat the particle beyond the ambient temperature. And the question is, okay, if you don't want to boil your your solvent, maybe this is 100 degrees or so, a bit more could be, because there's a small particle does not boil that easily. But you see, okay, that would be a third of about the T naught, yeah, and the prefactor is pretty small, like it's 1/2 or so, right? So we are down to affect an effect of 1/5 in the leading order. Now the second order is a delta T squared, and it's an even smaller contribution. And it depends now a bit on the relations of the solvent. You know, like here we have used some model of the solvent that is a Vogel-Fulcher law for the solvent viscosity. So the viscosity effects that also were subject of the previous question, they enter in second order, as you see. And so if you go to high temperatures, you may be able to see these temperature effects on the viscosity. And then you could, for instance, say, maybe this helps me to analyze my temperature dependent viscosity of my solvent, whether it's truly a Vogel-Fulcher law or maybe it's something else. Or you can say, I know my constitutive equation of the solvent and I want to utilize such a formula to get or check it or so. Nobody has checked, you know, these expressions too high for really high temperature gradients. Yeah, but you see, even if you heat your particle by 100 degrees, the second order term here would be small, right? And as soon as you start boiling the solvent or so, we would have to start a new calculation, and this would all break down, of course. Yeah. I hope it helps a bit what I said.